So one of the classic ways of describing escape velocity is using an analogy of what are called gravity wells. So Earth is sitting at the bottom of this thing that we call a gravity well because it's easy to sort of understand how hills work. And so we basically think of Earth as being at the bottom of a hill, and that's a gravity well. And then if we zoom out a little bit, Earth is sitting in a little gravity well, and it is sitting in the sun's gravity well. And so actually, we're a well sitting inside of another well. And if you zoom out even more, then there are gravity wells all over the place. So Earth has a gravity well, the moon has a gravity well, Venus has a gravity well, and the sun has a gravity well. And Venus, Earth, and the moon are all inside of the sun's gravity well. So it's gravity wells inside of gravity wells inside of gravity wells. So let's zoom back into Earth's gravity well. So let's say that you wanted to get out of Earth's gravity well. Well, how would you do that? Well, just like if you rolled a ball up a hill, and if you don't give it enough velocity, it will just come right back down that hill. But it's exactly the same as basically taking a ball and throwing it up in the air. If you don't throw it with enough speed, it will just come right back down. So these are very equivalent things. We can basically figure out how the initial velocity of a ball and the max height of a ball are related to each other. And we do these things using what's called the conservation of energy. We basically can figure out how much initial velocity we need to get that ball out of the well. And so the initial velocity of the ball is described in terms of what's called kinetic energy. And so something that is moving has kinetic energy. And then the well is providing what's called gravitational potential energy. And so the depth of that well sets the potential energy. So a very deep well has lots of potential energy. A very shallow well has very small potential energy. And so an object will actually leave that gravitational potential well if the kinetic energy is greater than the gravitational potential energy. And so you can figure out where those things are equal to each other. If you have just a little bit more kinetic energy, it will leave the gravity well. And so the escape velocity, using those equations, you get this equation. The velocity is equal to the square root of 2 times mu divided by r. And so mu for the Earth is the gravitational constant, which is just a universal constant, times the mass of the Earth. So it's g times m is equal to mu. And that's 3.99 times 10 to the 14th. And the radius of the Earth is 6,371 kilometers. And so if you solve for that equation for Earth, then you get the escape velocity at the surface of the Earth is 11,200 meters per second. So if something is moving away from the Earth with 11,200 meters per second, it will escape Earth and it will just never come back. If it's moving with 11,199 meters per second, it will go really far away from Earth, but eventually it will turn back around and it will hit the Earth. So let's say you want to escape the sun and you want to go to a different sun, a different solar system. What would that take? In this equation, the only differences are the mu and the r. So we basically can find a mu for the sun, which is significantly bigger than the mu for Earth, and then the radius is, let's say, the distance from the sun to the Earth, which is 1 astronomical unit, which is 1.5 times 10 to the 11th meters. So when you solve that, then you get the escape velocity from the sun at Earth is 42,000 meters per second. Now, we should note that the Earth is actually orbiting the sun, so the Earth is actually moving at 29,000 meters per second already, so you just have to speed up by about 12,000 meters per second and then you would escape the sun. So in summary, Earth is in a gravity well, which is in the sun's gravity well. The moon is in the Earth's gravity well, which is in the sun's gravity well. It's gravity well, gravity well, gravity well. To escape that gravity well, Earth's gravity well, you need the escape velocity. And the escape velocity depends on the mass of the planet and the radius of the body, so basically the size of the body. Earth's escape velocity is around 11,200 meters per second. You go faster than that, you escape. You go slower than that, you return to Earth. To escape the sun, you have to get out of Earth's gravity well first. So you need to move with 11,200 meters per second. And then you escape Earth, and you're essentially still orbiting around the sun. And then if you wanted to escape the sun, you would have to speed up even more. So you climb out of Earth's gravity well, you're in the sun's gravity well. Then you have to climb out of the sun's gravity well too. So it's actually really difficult to escape the sun.